Okay, so we're going to look at this problem. It's a 3 by 3 problem. So practice set 3 has a 3 by 3 problems. We're probably, I don't think on tests there's going to be a 4 by 4 system or anything higher. Not because they're not important, just because I think I can test on all of the key ideas that I want to test on just using 2 by 2 and 3 by 3 systems. So we're going to look at a 3 by 3 system, and again, when you're handed a problem like this, you should first find the eigenvalues and eigenvectors. Now the way we're going to do that is using Wolfram Alpha. So this is what we have. I put it into Wolfram Alpha, and it spits out these eigenvalues and eigenvectors, okay? And so pause the video or whatever and record them. Okay, now, again, so let me just emphasize that you are not going to have to actually yourself find the eigenvalues and eigenvectors. You are always going to be free to use Wolfram Alpha. And sometimes you'll get all eigenvectors, but sometimes it'll give you generalized eigenvectors. Now, you are going to have to know the difference between generalized eigenvectors and eigenvectors, okay? But you're not going to have to go through the mechanics of finding them. And you're going to have to understand that when you put in eigensystem to Wolfram Alpha, the vectors that it spits out, those vectors are all going to be linearly independent. And you're going to have at least some idea of how we use that linear independence. But you're not going to have a very good intuition about linear independence or anything like that. You just need to know how we use the fact that they're linearly independent to solve the problems. Okay, anyways. And I will illustrate that here. So we've got these different eigenpairs. Hopefully you've copied them down. And so again, the idea is that the vectors that Wolfram Alpha gives us, in this case, they're all eigenvectors. There's no generalized eigenvectors because all of the eigenvalues are distinct. Okay, we're going to be able to write any vector, and in particular the solution vector, we're going to be able to write it as a linear combination of the eigenvectors. Okay, so again, any vector in R3 can be written as a linear combination of these three vectors here that I'm pointing to. Any vector in R3 can be written as a linear combination of these three vectors. Okay, now since the vector that we're concerned in is a variable vector, meaning that it's a function of t, for every value of t, these coefficients are going to change. So that's why the coefficients have to be functions of t. And the differential equations that we end up are basically going to be, the differential equations that we end up actually quote-unquote solving are actually going to be differential equations for these coefficients. Okay, so let me just remind you that 1, 0, 0 is an eigenvector and the corresponding eigenvalue is 1. 0, 1, 1 is an eigenvector and this corresponding eigenvalue is -2. And 1, 0, 1 is an eigenvector and the corresponding eigenvalue is 3. Okay, so if we plug this vector, if we plug this into the left-hand side of the equation, let me use different colors. If we plug it into the left-hand side of the equation, what we get is C1 prime times 1, 0, 0 plus C2 prime times 0, 1, 0 plus C3 prime times 1, 0, 1 is equal, okay, now we're going to plug this into the right-hand side of the equation. Okay, if we plug this into the right-hand side of the equation, well, the matrix times 1, 0, 0 is just equal to 1. So this is going to be C1 times 1, 0, 0. Okay, the matrix times 0, 1, 1 is going to be -2 times 0, 1, 1. So this is going to be minus 2C2 times 0, 1, 1. And then finally, the matrix times 1, 0, 1 is going to be 3 times 1, 0, 1. And again, we know all of those facts because these vectors are eigenvectors. That's why we chose eigenvectors. There are many different bases for R3, but we chose a basis of eigenvectors because when we plug it into the right-hand side, we get this very nice formula. Okay, now we can do this compare coefficients things. Okay, so if these two vectors are equal, if the green vector on the left is equal to the red vector on the right, what this tells us is that C1 prime is equal to C1. It tells us that C2 prime is equal to -2 C2. Actually, I'm going to write this as a row instead of like this so I can do everything on one page. Anyways, then we know C2 prime is equal to -2, is equal to -2 C2. and we know that C3 prime is equal to 3C3. Okay, and we know how to solve each one of these equations. Sorry, there should be a minus there. And we know how to solve each one of these equations. These are all linear first-order homogeneous equations. So this is C1 of t is equal to some constant a1 times e to the t. C2 of t is equal to some constant a2 times e to the minus 2t. C3 of t is equal to some constant a3 times e to the 3t. Okay, and now we just plug in these expressions for C1, C2, and C3 into this set of equations here. And we get that x1 of t, x2 of t, x3 of t is equal to a1 e to the t 1, 0, 0 plus a2 e to the minus 2t times 0, 1, 1 plus a3 times e to the 3t 1, 0, 1. Okay, and that is the general solution to this system of equations.